Welcome everyone to today's
Hi.
webinar titled Autonomous Lunar L1 Halo Orbit Navigation Using Optical Measurements to a Lunar Landmark, based on a paper recently published in Navigation, the Journal of the Institute of Navigation. Today's webinar is presented by Dr. Mark B. Hinga, one of the paper's authors, and we're glad to have him with us today. Dr. Hinga has earned a PhD from the University of Texas at Austin and has worked for 14 years at Sandia National Laboratories and has currently been at the Air Force Research Laboratory for 4 years. Dr. Hinga's research interests include spacecraft auto navigation for cis and translunar orbit trajectories using optical measurements to lunar landmarks. Following today's presentation, we'll accept questions from you, the audience, and you can enter those questions in by clicking on the Q&A button in your viewer. We'll now turn the time over to Dr. Hinga. Mark, you can take it away.
Okay, thank you, sir. So thank you very much for attending this webinar. I'm very happy you came. My name is Mark Hinga, and also involved in this project was Dale Williams, a grad student at Purdue University. So I'm going to be here only, he's not here, so I give the presentation, and the title of the presentation is Autonomous Cislunar Navigation Using Optical Measurements to a Lunar Landmark. Okay. So the outline is, whoops, wait a minute. So the outline is we're going to formulate the problem. We're going to discuss the overview of the simulation architecture, talk about the observations and formulation of the navigator. It's a two-phase algorithm. Then I'll talk about the experiments. It's about the one southern halo, about the L1 Lagrange point. This is performed in the circular restricted three-body problem. Then I take objects, geosat, LEO satellite, asteroid, and then a target for the moon center, Tycho Crater. And at the end, we'll do discussion and conclusion. So the problem scenario is a Halo L1 spacecraft. I like to think of it as the Apollo CSM module. On the left side, you see the circular restricted three-body reference frame. The true southern blue orbit is the simulation truth, and the red trajectory is the Kalman Filter solution. You can see that it converges at about 4 days. Using angular measurements to whatever object you're looking at. And on the left, you see it's 2,100 kilometers perilune. Apollune is 20,000 kilometers. The period is about 8 days. And Jacobi constants there, about 3.01. And on the right side, we see the same orbit, but expressed in the Earth-centered inertial. And we see here's a asteroid that's part of an object that we use to navigate off of. This little yellow circle here is a geo satellite orbit. And if you can see here against the Earth, an iridium green orbit, this green orbit here is the moon. The blue trajectory here is the truth. And the direction of flight is in this way. The red, again, is the estimated trajectory that the navigator provides. So next slide. So how do we do this? Well, one possible solution is we use angle unit measurements. That is geometric line of sight unit vectors. There's no radiometrics going on here. And we might think about looking at asteroids, moons, satellites. And the requirements are generally you need to have a camera of sufficient quality, a good knowledge of this orientation, knowledge of the location of whatever object you're looking at. We turn to JPL's ephemerides. List, for example, this one, we use DE421. Also, I forgot to mention this slide, time. You got to know what time it is. Okay. So overview of the simulation was custom built and C++. We have a simulation, a navigator, and a guidance. We got guidance algorithms in there. I call it the Hinga Space NavSim. It's been in production now, or not production, but development for 10 plus years. In this simulator architecture, we have a custom built IOD filter that is initial orbit determination batch filter. Can include stabilization, but it's not here in this study. This batch filter was performed in this simulation study in the two-body frame, or rather the frame in which the two-body motion is considered only. So all propagations are carried out either in the J2000 frame, that's in the batch filter, And for the navigator, things are carried out in the CR3BP. On the left side of this, you see a little picture of the ECI. On the right side is a typical picture of the CR3BP. This picture here, this diagram I got out of Volato, and that describes the Earth-Moon system. Okay, let's go to the next slide. So the model of observation, just want to briefly describe it, and it's quite simple, actually. So again, these are unit vectors for the row 1, row 2, and row 3. Those are in blue. Okay, and the position of the asteroid, for example, is here, this dashed capital R1, R2, R3, the dashed black lines. These positions in the either J2000 or in the CR3BP are given by the JPL ephemerides. And the position of the CSM here, this particular spacecraft, would be unknown. We don't know what that is. We're trying to estimate the red values, R1, R2, R3. These are unknown. And these row 1, row 2, those are vectors, but they are formulated as unit vectors. So the person inside the spacecraft or the camera would look at the apparent center mass of the asteroid. The camera would put the crosshairs at the apparent center mass, form a line of sight unit vector, multiply by -1 to get this unit vector to point from the asteroid to the spacecraft. And then we estimate the scalar range between the two objects. And that's about it. Here's another picture here that describes how the changes of the positions evolve. Whoops, hang on, sorry. And that's about it. It's very simple, and we do triplets of, we have measurements 3 at a time. So this is, again, this is the two-body problem, inertial batch filter. We are using the classic Gauss. Here's, oops, hang on a minute. This is Professor Gauss himself on the right side here. These are the coplanar system of motion measurements, the Gauss equation. You've all seen this before, I'm sure, so I won't go into too much detail. But the row, you can see the row K, row K, row K here, row 1, etc. These are the scalar distances that we don't know, but we do know the unit vector values. And the coefficients here, we calculate through FNG series. This simulation uses the second order approximation of these coefficients. Also, we can do the actual precise coefficient calculation as well. All right, so since I mentioned we'd have a triplet of measurements that are taken 3 at a time, we have a sliding window such that every new unit vector adds into a new triplet. So we have a sliding window, and we see this system of measurements. We have a tridiagonal matrix. Here, this column vector here is the unknown scalar values for each unit vector, and the right-hand side is basically the position vector of the asteroid in this case, or whatever object we're navigating off of. In summary, this is a solution of the normal equation we form here, which is a happy result because we have real and symmetric, therefore it's positive definite. Therefore, we had a good chance of it converging when we get close enough to the truth. Okay, the second phase 2 is the Kalman filter, and that is performed in the rotating frame. So the batch filter provides the initialization of the Kalman filter in the rotating frame, and it usually is good enough to get it kick-started, and then it converges after time. We have a predict phase, an update phase. I won't read that all off because most people know what this, it's in their bread and butter. They know what that is. So, and oh, by the way, this is Kalman himself on the right-hand side. See the picture here? Next slide. Here are some more equations. We've all seen these things, but let's think about this matrix H. I found this to be an interesting part of this Kalman filter that's helpful in our study. We'll talk about that later. So this is the sensitivity matrix H. That is, it relates the change that we see in the observations to how the estimate in the state vector would change. And oh, by the way, we're estimating the error state, not the state itself. So we estimate an error and we add the error to the state to get a better knowledge of our state. So here the state actually is x, y, z, x dot, y dot, z dot, that's position velocity. And that is, again, in the rotating frame, the Kalman filter. And the observation here, Y, we have unit vectors, geometric line of sight unit vectors, and we break it down into components, Lx, call it Ly, Lz, unit vectors here. And we take the partial of this observation model with respect to the state, see here, and we get this partials matrix. Notice that the 3 columns on the right are 0 because this unit vector can see no velocity. It only sees position. So this is 0 here, these 3 columns. Okay, next slide. So the model of measurement also included noise. And Dale Williams is the one who came up with the code that coded up the perturbations in the right ascension. You can see here from the point of view of the camera and the platform frame of the observer, and the declination perturbation. So here we have a Gaussian perturbation. He has it in this form. We have alpha. Whoops, I'm sorry, I shouldn't have touched the mouse wheel there. So this alpha is right ascension. This delta is the declination. We have the true values, and he corrupts them in this manner, just adds it. And we chose a 0.1 degree, 1 sigma distribution for error on the line of sight unit vector measurements in this study. Okay, and next slide. So experiments, we did 50 days was the timeline. The knowledge of the navigator is perfect, okay? It knows everything about the circular circuit-through body problem. So we propagate the truth also in the same frame. We have experiment results with and without measurement error. We navigate off different bodies, various, one asteroid, some satellites, and then some lunar objects on, well, the sun of the moon, Tycho Crater. Then we do a tempo check, varying the time between the observations, and then we, for the whole simulation, it's basically 1 revolution. About the L1 halo is 8 days, but we do, you know, as much for 50 days. And all Jacobi constants in navigator and simulation, I want to mention, change less than 10 to the minus 15. So that means the very first one at 0 and the very last one, 50 days, the difference was less than this number. So that helps us be confident in our simulation that the our equations of motion, etc., were good. We believe them, but so it's a necessary condition to be confident, but it's not sufficient to prove that we're doing it right. But at least we are not completely wrong. We know that. Assumptions: we start off lost in space. We have no knowledge of the state. It's cold start. So we still know the time, but we have no idea where we are. Only assumption is that we're 2-body motion about somewhere about the Earth. We assume the constant line of sight to the observed space target is it's constant. It's center mass of the target. There's no interruptions. We don't have to worry about sunlight getting in the way. And the total attitude error and ephemeris error is summarized in our so-called measurement error. We're just trying to assume that all errors can be accumulated and represented as in the 0.1 degree standard deviation Gaussian distribution in the measurements. Okay. So here are the experiments. So we did a LEO satellite, a geosatellite, 1 asteroid back in 2014, the Moon Center, which is interesting, and then we did a lunar landmark, so-called Tycho Crater. Then we did a tempo investigation. We had measurements spaced out by 1, 10, 30, or 60 minutes. And then we assumed the navigator can always take measurements. No worries about issues about not being able to take a measurement. Okay, so here's one table that describes the happy results for no measurement noise. We want to do an experiment, no measurement noise, 1 minute interval just to see what's going on, inertial batch solution. And we simply take the difference to truth because we know the truth. We're simulating the truth. So this column here is the geosat object that we navigated off of. This column's LEO, asteroid, Moon Center, and Tycho Crater. Point is that the Kalman filter always converges in each case. So remember, we don't know where we are. We take measurements, at least 10 in this case, maybe 15, and we get these solutions with this initial difference to truth. Okay. Again, we do it with measurement noise, same with the 1 sigma error, 10-minute intervals. And we do the initial batch solution difference to truth, but then just the geo and the asteroid navigator objects all diverge. But looking at the LEO satellite, the Moon Center, and the Tycho Crater, all of those converged. It took a while, something on the order of 35 days, but they still converged. And so I call that a happy result. And so it works, at least in this study. Okay. So let's look at the performance in a different way, so-called phase 2 navigation position error. So that's a magnitude position error. The left plot here shows a distance to truth in kilometers versus time. So this shows that the asteroid here, after 10 days roughly, begins to diverge as an object for navigation, becomes useless, and the other objects seem to do well. So let's remove the asteroid and look at the right plot here, position error. With no asteroid, we see that the LEO GEO and the Tycho Crater Moon Center all do pretty well, but looks at the pink and the black, the moon targets do quite well, and they do fairly well after some 43, 44 days. Yeah, but the rest of them do pretty well, but it seems that the lunar targets are going to be winners here. They're going to be the best candidates. Okay, so let's look at the, again, position error, just looking at the center moon, Tycho Crater, little focus, zoom up of the same plot. We see here we have happiness. Tycho Crater looks like is the best target based on this result for distance to truth. Here's a picture of the Plato crater here and the Tycho Crater here, just for convenience. So it looks like the Tycho Crater is best. Okay, next slide. Let's look at the velocity solution, because don't want to just look at the position. Here we have in the left plot here, distance to truth, meters per second, scalar magnitude versus time. For the 4 objects, we see here that the lunar objects tend to perform better with respect to true error. In other words, the distance between the estimate and the truth. On the right side, this again, the right side is directional error. So we'll look at the error in terms of the directional error of the velocity. So distance to truth in degrees, we see that after, say, 20, 35 days, let's say 35 days, all objects perform fairly well as far as being 1 degree or less to distance to the truth. The lunar targets still perform better. Takes a little while for them to converge, but it's still success. Okay, so we declare that the moon wins as the best target body. And we like the Tycho Crater. Now we're going to look at the effects of tempo between the measurements. So if we look at the position error as a magnitude, as a 1, 10, 30, 60 minute steps, looks to me that the 1 and 10 minute tempo, those values look better than the 30 and 60. The 60 becomes not so good after a while, but then it converges quite well. But let's zoom up on the right side here, distance to truth in kilometers. It looks like the 1 minute looks like it eventually wins out over the 10, although the 10 is not bad. Okay, so you could choose 1 or 10. Let's look at the velocity magnitude. Again, we see similar behavior with 1, 10, 30, 60 tempo. Again, 1 and 10 minute measurement steps do well. If we looked at zoom in on the 1 and 10, we can see some behavior here. Looks like the 1 minute may look better than the 10 minute. So next slide, we'll look at the directional error. We see on the left side, distance to truth for all 4 measurement tempos. For directional error, same results. Zoom in on the right side, same results. 1 and 10 seem to be neck and neck to make it to the finish line for the best tempo measurements. So let me just say, it looks like 1 or 10 are the best measurement tempos to take. Let's look at the Frobenius norm, the H matrix I mentioned before, the Frobenius norm of the sensitivity matrix H. So if we look at all the asteroid, all the objects, asteroid, LEO, GEO, center moon, Tycho Crater, we like to see the Frobenius norm, that is the magnitude of the matrix, be large. Small values are not so helpful. So if you see the pink and black, the lunar targets are larger for Frob norm. than the other objects here, the asteroid, Leo, Geo. So we can see that the fast-moving apparent motion that the satellite will see of the moon produces larger Frob norm of the H matrix, whereas the distant targets don't move as much from the perspective of the observer, not too much, therefore the H is smaller, the magnitude of it. So in summary, the lunar targets have a larger H matrix, more useful info relating OBS to the state estimate. So that's a happy result. So let's look at the no measurement noise just real quick for Venus norm of the asteroid Leo Geo. You see the asteroid here is coming down quite quickly. It just says, okay, you're right. It's not very useful for 10 days. These guys up here, the Leo Geo, they stay about the same, about 1, less than 2. On the right side, the lunar targets, quite large. They go all the way to 70, much larger than the other objects. So in summary, the asteroid becomes useless after 10 days. Lunar targets are much better. We can see these spikes of the matrices of H, the Frob norm, occur at 12, 20, 28, 36, 44, and that is precisely according to the passages at perilune. Passing perilune is very good to help the navigator converge. Okay, let's look at some Kalman gain. Just really quick look at this, the Kalman gain performance. We can see the spike in the Kalman gain of the navigator occurs every 8 days, 12, 20, 26 roughly, 35, 45 for the tempo of 1, 10, 30, 60-minute ob steps. We zoom in on the 1 and 10 on the right. We see the performance of the 1 and 10 Kalman gain. Again, these spikes happen right at Kalman gain comes being very, very large, close to perilune. And then precisely at perilune, the Frob norm of the H matrix spikes to its maximum. So this just gives you a feel what's going on with the Kalman filter as we're approaching perilune. That's the point of this. Right. So how much time I got left? I got 8 minutes. So in conclusion, we use an inertial batch filter, initial orbit determination solution, cold start. So we just use the traditional Gauss method to start cold start lost in space. So we don't know what the state is at all. We just take these measurements and we get a good estimate, good enough to kick off the Kalman filter. Kalman filter is able to maintain track on the vehicle state in the rotating frame. So it's good enough to make it converge in a rotating frame based off a non-rotating frame. We have the GeoSat navigator never converged. It's not good to try the Geo 1. The Leo, it does converge, but I wouldn't rely on that one. The asteroid, it works well, but only for a few days. So if you're going to use it, it's got to be right there, and it's only lasts for, I say 10 days here, but it's probably only good for 1 or 2 days. So using the moon targets is very good. As I mentioned, because the Frob norm of the H matrix gets large H, large Kalman gain is very good for the Kalman filter to update the state. Gives you happy results. We can, again, the navigability, it's a tongue twister there, is the spacecraft is significantly influenced by the H matrix. In this period, we had a warm-up period of about 5 days, which was, that's the way it goes. It took a long time. It took a long time for it to converge of 35, 42 days, but it still converged. We decided that the measurement cadence is obviously affects the performance of the navigator, and 1 or 10-minute time step is desirable, but I think I would go with 1 time step measurement cadence. So let's see how much time we got left here. We have 6 minutes. So I'm ahead of schedule, it seems. So also, I want to mention in the phase 1 of this study, there was no guessing in the initial part of the batch filter. So there's no guessing for the range of the unit vectors to be applied, the range applied to the unit vectors between the object of navigation and the observer. So we start that value at 0. So if you can guess 0, this will converge. And the other assumption we didn't make was the class of either the observer or the target, but we did assume that it's somewhere about the Earth and not knowing about the moon. Also, I want to mention that there's no solving of the eighth order polynomial as required in the original traditional Gauss. This no solving of the eighth order polynomial and guessing at zero was a method invented by actually Paul Hergé back in the late 40s, and then Motari at Texas A&M. He developed that and made it very useful and reliable. And I'm implementing that algorithm from Motari in this batch filter to get the Kalman filter to be initialized and then to converge. If we're trying to do this from the ground, though, if you're doing an observer from the ground, I mentioned you have to use the eighth order polynomial. But if you're a space-based observer, then you don't have to use the eighth order polynomial, and you can just use the Motari Hergé method and guess zero for the scalar range between the observer and the object of navigation. Also, this method solves for exact F and G coefficients, but I found that the second order approximation does just as well for the most part. So you don't really need to use the exact solution for the universal variables, just the second order approximation of the F and G series. So I try to get as much said in this with 4 minutes left. I hope I made everything clear enough for it to be understandable. So I guess I'm open for questions right now, if there are any. I just want to say thank you to Dale Williams for his great help. He's a grad student at Purdue. That guy is brilliant. Wow, is he smart. And I'm going to say thanks to my current boss for her support in doing this, and also the U.S. Air Force for helping me do this too, and letting me do this in my day job. And I want to say thanks to my wife for helping me getting this computer set up. She's the computer scientist. Couldn't have done it without her. And also the help from Rick and Beth. They did a great job. I also want to say thank you to the ION folks, all of them, for allowing me to present and allowing the manuscript to be published. It has been a privilege. And I hope to give another webinar in the near future. And so thank you very much. Appreciate your time. I hope there's some questions. Rick?
Great, thank you so much.
This
is great. So if you'd like to ask a question, Dr. Hinga, you can click on the Q&A button in your Zoom viewer and enter your question there, and we will address those. So let me just start with a question here, which is why is autonomous cislunar navigation important? Oh,
yes, because there are going to be so many missions up to the moon. They need to be able to be independent and not rely on help from the Earth ground. There'll be so many satellites up there. They'll need to be able to live on their own and be independent. Otherwise, it's going to be too crowded for the ground system to help them. That's
okay.
One reason, and it's cheap. So we open up the field to smaller payloads and people with less money to perform science experiments and things.
Yeah, great, interesting. We do have a question in the Q&A. If you want to, you may want to look at this one because there's some background information on that from Carrie's son.
Yeah. Oh yeah. Carrie's son. So listen. So I guess people can see the question. I'll just read it out. Instead of Frobenius norm, one can look at the observability Gramian. Yeah, the observability. So that may be the condition number. That's good too. If the condition number gets too big or small, that'd be a good way to see how good your measurements are, how much information is in your measurements. That's helpful to the estimate of the state. Let's see, this is similar to F norm, but the advantage is that there are more ways to, okay, yeah, that's good. It's similar to the Frobenius norm, but the advantage he or she says is there are more ways to analyze trajectory and determine which one is better. Right, I'm learning about how to better get a Kalman filter to perform, so that's a great comment. One from Dr. Grasso is on slide 15, lost in space. How accurate does the clock have to be? I would guess on the order of, maybe the order of perhaps milliseconds, but I would say microseconds are probably more likely, maybe 100. I'm guessing maybe 10 microseconds. I'm not sure, but it's on the order of microseconds. A great question. Professor Russell is there. Yeah, let's see. Hey, Ryan, thanks for coming. Question 1, why not just solve the whole problem in the inertial frame? I'm not sure the rotating frame helps in this case. Question, why not just solve the inertial frame? Yeah, that's a great question. That's something I would like to do. I don't have a good answer. Why not? That's a good point. Question 2 from him says, what if you're in a 3-body dominated orbit at the beginning, lost in space? Yeah, if that's the case, he says, if I'm a 3-body dominated, in other words, I think the 2-body assumption would just break down. It wouldn't work. You get hyperbolic answers, and it wouldn't work. I'm guessing it wouldn't work. So Christopher Grasso, Dr. Grasso asks another question. Can you solve for time simultaneously? That's a great question. I don't know, but I bet there is a way you can do that. I imagine there would be a way. I don't know, but if you had, I imagine there, I think Dr. Grasso mentioned to me once upon a time, you could use star fixes as they appear out from behind the moon. You can figure out what the time would be. But I think the model I have implemented now, I could not solve for time simultaneously. So I think hopefully that answered the question. My next effort would be to do everything in the ephemeris model world, in other words, inertial frame, and solve everything in the J2000. Hopefully did that answer the questions? I hope it did.
Give it a moment here, see if there's any additional questions or any
Okay.
follow-up.
All right.
Well, that's great. Thank you for your presentation today. We appreciate your time and preparation in providing this webinar for us. And we encourage our viewers to go view the full technical paper, which is available on our journal website at navi, that's navi.ion.org. And we remind you a recording of this webinar will also be posted within the next few days. So thank you for joining us. And Dr. Hink, thank you again for your time today.
Thank you very much. It was great. I had fun.
We'll do it again. Thank you. Bye-bye.
Thank you. Bye-bye.